In this lecture, we're going to look at an example of a geometric proof a geometric theorem that we can prove using strong induction. And what we've got here is a statement about simple polygons where we know the number of sides, right? N is an integer, obviously, right? Got to have an integer number of sides. And n is greater than or equal to 3, which is actually the smallest size for a polygon. It's a triangle. And in this case, with this kind of polygon, we can triangulate it with n-2 triangles. Now, I know there's a lot of geometry terms going in there that you may not remember or you may never even heard before. So, well, I don't want to get bogged down in geometry definitions. We do need to talk about a few of them so we're all on the same page talking about the same thing. So first, a simple polygon has no two consecutive sides that intersect. So this one down here, the first one, that is not a simple polygon because these two diagonal sides here cross at that point. So that's not the kind that we're going to be talking about. We're going to be talking about ones like all the other ones over here. Right, so every simple polygon divides a plane into two regions, an inside and an outside, right? It's pretty intuitive, but honestly, that is a surprisingly difficult thing to prove. But that's a geometry concern that we're not going to worry about. We're going to assume that yes, there is an inside and an outside to every polygon. Excuse me, every simple polygon. A diagonal is exactly what you think it is. It's a segment whose endpoints are two non-consecutive vertices, and an interior diagonal is one that lies entirely in the interior of a polygon. That's all probably pretty familiar so far. Triangulation refers to dividing a simple polygon into triangles by drawing non-consecutive diagonals. All right, so for example, I've got this, how many sides are there on this thing? 1, 2, 3, 4, this pentagon here, right? If I draw diagonals here and here, that divided this pentagon into 3 triangles. That's what we mean by triangulation. All right, so now look at this example. I've got two of the same polygon here. If I draw, let's see how we can do this. I'm going to draw here, here, and here. That's a triangulation, right, into 4 triangles. Or I could do this. Could do this, and then this, and then this. So these triangulations are not necessarily unique. Yeah, there can be more than one way that we can accomplish this. So I've got our theorem here again, and we're going to prove it using strong induction. Our basis case is going to look at n equals 3, since that's the smallest number the theorem talks about. If n equals 3, then the polygon is itself a triangle, which can be triangulated by itself. You don't need to add any diagonals to make that happen. So next, we need to consider the inductive step. In this part, we're going to assume that the theorem is true for all polygons with between 3 and n sides. And we have to show that this means that it's true for a polygon with n+1 sides. And there's really going to kind of be two parts here. First, we're going to have to show that the triangulation exists. And then we're going to show that the number of triangles we get is 2 less than n-1. It's 2 less than the number of sides. So let's start by letting P be a polygon with n plus 1 sides. Something like this. Now, draw an interior angle, an interior diagonal. Draw interior diagonal, and let's call it AB. So I'm going to draw it here. Now, note that AB splits P into two smaller polygons. So call the two resulting polygons Q and R. So P is the big one, Q and R are the smaller ones. Now, notice that Q and R both have at least one side less than P does. So if we let S be the number of sides of, let's let S be the number of sides of Q, and T the number of sides of R. So let's see if I can't get that in there. Let's say P has n plus 1 sides, Q has S, and R has T. Now, we know that S and T are both between 3 and n. So that means that Q and R are both covered by our inductive hypothesis. So from this, we know that P can be triangulated by taking the triangulation of Q and combining it with the triangulation of R. So at this point, we've shown that the triangulation exists. Right? Now, we need to look at the number of sides. Right? So, again, applying that inductive hypothesis, Q can be triangulated with S minus 2 triangles and R with T minus 2 triangles. Now, this means that the number of triangles to triangulate P is equal to S minus 2 plus T minus 2, which is S plus T minus 4. Now hold on to that for a minute and look back over here at my diagram. If I add up the number of sides in Q and R, that is going to be 2 more than the number of sides in P. So that's going to be m plus 1 plus 2. Right? And then to think about why, right? Every side of P is a side of Q. Excuse me. Every side of Q is a side of P. Every side of R is a side of P. Plus, Q and R both have that middle diagonal. So that kind of bumps the number up by 2. All right. Now, here's what I want you to notice. This means that n plus 1 is equal to S plus T minus 2. Now come back over here to my count of the number of triangles I needed. S plus 2 minus 4 is S plus T minus 2 minus 2. And I know it may seem a little odd, but look, s plus 2 minus 2 is n plus 1. So put that in here. This is n plus 1 minus 2. And that's what I need to show for the count. Right? The required number of triangles to do this triangulation is equal to the number of sides, that's n plus 1, minus 2. That's what I needed to show for the part about the count, the number of required triangles. Okay, so let's take a step back here and think about why strong induction rather than just mathematical induction was the tool for this job. When I drew this diagonal here, I know I made two smaller triangles, but I didn't know how much smaller, right? And this is why it wouldn't have been sufficient just to know that I could do the triangulation with polygons one side smaller. I had to know it was possible to do it with any smaller size. Okay, so that's a nice little geometric proof. So in the next lecture, it's going to be our last example using strong induction. We're going to go back to something we talked about earlier in our number theory discussion. In that earlier conversation, we talked about writing decimal numbers as binary numbers, and we talked about how that was particularly important for applications in computer science and doing computer-related things. Well, we made a pretty big assumption there that it was possible to do that. In other words, we kind of assume that every integer has a binary representation. That's the kind of assumption mathematicians aren't very fond of. So we're going to resolve that in the next lecture. We're going to show that, in fact, every decimal integer does have a binary representation.